Hi, I'm Lisa. I'm here to talk about balancing books. The way this talk came about is back in December, I had a chance to catch my breath after a complicated year and got to thinking about some things. And in January, I had an unusual chance to spend some time with a bunch of the smart people who worked on contracts while not being pressured to run from vote to vote in the committee. And over lunch, I told them about this. People got very excited, much more so than I expected. And I get home, my inbox is blown up, and I'm thinking, I've got to put this into a talk just so I can fend off the email. So that's how this talk came about. Sorry if some of the material is a little rushed, particularly the syntax, very early days. Please focus more on the concepts than the specific syntax. So I want to tell you a story about a young computer language. They come up with certain rules that they would like functions to follow, that it's good to follow. And they say, look, if your subprogram, a piece of your program, follows certain rules, it gets a gold star. And the gold star is an objectively valuable thing. Almost everybody wants a gold star. The people who don't want a gold star are just surly teenagers who don't want to follow rules. Everybody should want the gold star. So what happens? Well, there's a certain amount of code that's already written and pretty much no gold star. They didn't even know about these rules. But as the language evolves, a lot more code gets written. Some of the new code doesn't get the gold star, but most of it does. And this language is in a great position of having a ton of gold star code, which, as I said, objectively valuable. This, of course, is the story of const correctness in C++. We've got a lot of const correct code out there to the point where you expect this of any code that you get in the wild from a vendor. Only surly teenagers and people who are desperate to interface with this terrible code at the back are going to write code that's not const correct. I think you could argue it is also RAI resource management in C++. We do a much, much better job of managing resources than we did before C++ and its constructor-destructor model was introduced. It is also, I think, the story of borrow-freeze correctness in Rust. Rust is a language that has something called the borrow checker, which checks for a certain sort of correctness, and having that correctness makes your code good. It's a good property to have, and there is lots of borrow freeze correct code being written in Rust. That's great for them. So, excuse me, the air's getting to me a bit this morning. So, in the C++ world, when we see something like this, we see that another language has a good feature. There is one thing we do. We take it and make it our own. We are an accretive language. We steal all the best features we can from other languages, and that way we can get pretty much anything but sensible orthography. I don't think sensible orthography is compatible with being as accretive as we are. So we see this, we want to steal it. Lots of people are interested in stealing this. I should say right off, I am not an expert in Rust. If I say something about Rust, don't believe me. I'm going to stick to saying things about C++ if I can. But people on the C++ committee want to steal Rust's features. I can say that. Here's another story about an older computer language. Older computer language introduces a program where if your subprogram follows certain rules, it gets a gold star. But there's a ton of code out there, ton of great code that works perfectly, and some that doesn't. But a ton of great code is out there that does not follow the rules. And even worse, interfacing to it might mean that you can't follow the rules. What happens then? Well, over time, you get a little bit of gold star code. But you're not going to get into a situation where the gold star code dominates for a very, very long time. And that's just one of the perils of being an old language. You have a lot of investment in old code. And nobody wants to take old code that works perfectly well and rewrite it just to follow some newfangled rules. So this is pretty much what we think Rust-style borrow-freeze correctness would be if we copy it directly into C++. People would be forced with choices like, do I write code that follows the new rules, or do I use the standard library? And using the standard library is going to win out a lot of the time. And there's a lot of functions that you can't, in our standard library, that you couldn't use under Rust's rules. So this has been a problem for stealing this feature. Now, as I said before, I've been working a lot on the contracts feature in C++, which is voted into the draft in Hagenberg, so hooray. And here is a thing to know about contracts. Contracts facility in C++ does not provide that feature. Some people are really annoyed at this, I think quite unfairly. We never intended to provide this feature. We provide a different feature. It's a good feature. But we never intended to provide this. We never said we would provide it. And yet, somehow, a bunch of people have been upset that we didn't provide it. The Unicode team didn't provide it either. The parallel algorithms team didn't provide it, but they're upset with us. I've been a little annoyed at that, so it pops into my mind, and I spent some time thinking, well, could it in a future version of C++? Not the first time I'd gone down this path, but things took a turn. So let's take a look at what it means to do a correctness feature in the contracts style. So first, it means we are going to give users a choice between efficient trust and redundant verification. This is the fundamental choice that contracts is about. You can trust your code and have it run efficiently, or you can verify your code and it will be less efficient because verification is always redundant. You can't generally have both of these. You have to choose. So we give people that choice. That's what contracts is about. That's what writing an assertion is about in C++. But we let you make the choice outside the source code. You don't make it when you're writing your code. When you write the code, you write the assertion in order to defer that choice, to say this gets to be made at a higher level later on outside the source, and typically made when you compile the source. And if you change your mind, you can change your decision just by recompiling the source with different parameters. So that's how we make the decision outside the source. We also insisted that the choice be granular at the translation unit level or smaller, because if you tell people everything in the world has to make the same choice, it becomes very hard for them to flip that switch. They can't. They look at it as like, oh man, I have to recompile the world to make a different choice. They don't want to do that. So we're going to let them make the choice at a translation unit level or smaller, and we are going to make the choices for different translation units independent. You don't have to care how some other person's translation unit was compiled. That's particularly important in the case of libraries, because you might not have had a choice about how that library got compiled, and you don't want to have to find the verifying version of the library in order to get your parameters to that library verified. And you certainly don't want to boot into the verifying version of your operating system in order to get your parameters to an OS call verified. So you get to make your choices independently of other translation units, and at the boundaries, either the boundaries between translation units particularly, but if the choice is more granular, even in between functions, either side can insist on verification. That is, if something is going across the boundary between a caller and a callee, the caller can insist on verification in their translation unit, or the callee can insist on verification in their translation unit. And that's how we ended up with a model like this. You can think of pre and post conditions as having two faces. There's the caller facing preconditions are the ones that's the caller's compiler seeing the preconditions of the functions and deciding how to compile them. The callee facing preconditions are the callee's compiler seeing the preconditions and deciding how to compile them. And we let both be checked. So that's our model. If nobody trusts anybody, if everybody insists on verification, it's possible that things might get verified twice. That's how it works in the real world too. If I travel internationally, my passport gets checked going out of one country and it gets checked again going into another country. There's not enough trust that my passport can only get checked once. And that's okay. We accept that because we think the verification is more important than trusting the other country in this case. So that's pretty much the contracts model, but there's a little more to it. And that's that the assertions, the contract assertions, are verified by inspecting runtime data. There has to be data for them to work on. They look at the actual values of your variables. And the verification is hidden from the code being verified. That is, the flow of the verification needs to be, we want to be one way. We want the verification looks over what the rest of the program is doing and signals if something is going wrong. But the program doesn't get to ask whether things are being verified. You can't ask whether the inspector is at the plant today. You can't ask whether the secret shopper is in the store. You want to write your code to do the right thing, whether the inspector is there or not today. So these mean that any data that we need has some really kind of weird properties. If we want to go beyond the values of objects, which are there where we can inspect them, we need to find some way to make runtime data that is hidden from the code in our translation unit and is not reliant on any other translation unit because we can't control their choices. But it still has to affect the outcomes of verification. And that's where we've gotten stuck before. It is hard to see where we could find some data like that, how we could store it, because we can't change calling conventions without agreeing with other translation units. We can't change the sizes of objects. We need to find some place to store it where it doesn't even bother our own translation unit. And what I realized is that I know a system that has these properties. I learned it from my mother. She learned it from her grandmother. It was an old system, even then. It's double entry bookkeeping. We don't actually know who invented double entry bookkeeping. We have a ledger from Florence in 1299 that uses it, but quite possibly it had been in use in some time. We don't have that many ledgers from before 1299. So it was good enough for keeping track of the goods that a Florentine merchant owned, and I think it's going to be good enough for us, because the secret to double entry bookkeeping is that every transaction is entered twice. It's not actually a well-kept secret. It's right there in the name. So one entry is a debit indicating that something is leaving one account, and the other is a credit indicating that the same thing is entering another account, because every exit is an entrance somewhere else. And as Tom Stoppard's player would tell us, that is a form of integrity. It is the form of integrity that bookkeeping uses. So in this model, double entry bookkeeping fits very nicely. We can have each translation unit keep its own ledgers. Each function can have its own accounts. And as we leave in a function call, as we go outward, we record debits to the caller. But as we come inward, we record credits to the callee. As we return from a function, we record debits to the callee and credits to the caller. And neither function needs to see the other one's books to do this. They just both have to be able to calculate the debits and credits. And that space in between functions that pre and post conditions uses is also the space where you can put debits and credits. So it's great for keeping track of these sorts of things that have an almost physical reality, even if you can't see them. They have this property that they're not like knowledge. You can't duplicate them. You can only move them from place to place. And if you give it to somebody else, you don't have it anymore. Like the goods in a Florentine warehouse. Or the debts on a Florentine ledger. Not necessarily something you can see, just something you can keep track of. So what do we have in programming that is like that? Well, I'm going to take a page from some of my earlier talks. Say, well, here's a situation we might find ourselves in. Our program, represented by the bald guy, wants to have a variable with the value 5. And the computer, the implementation, the outside universe represented by the robot here, says, okay, made a variable, its value is 5. But that's not actually what we really wanted, because we actually don't need the value to be 5 now. We need the value to be 5 at some indefinite point in the future. We want an assurance that the value will continue to be 5. So what we want is for the computer to make us a promise. And in this case, I am symbolizing the promise that the computer makes to us as these octagonal blue tokens. So the computer promises us that the value won't change, and we get a token representing that promise. And as long as we hold that token, we know that the computer will stick by its promise and act as if the variable has value 5. Of course, we may get tired of 5. So if we want a different value, we'll return the token to the computer. It can change things and issue another token. That's what we're going to keep track of in the ledger, is these tokens. It turns out this sort of relationship was studied by legal scholar Wesley Newcomb Hofeld back about a century ago. And he tried to come up with a uniform terminology for how to discuss these relationships. And in his terminology, what we are doing here is entering into a right-duty relationship with the computer. Our program holds the right to have the computer act in a 5-ly manner. The computer has the duty to act the 5-ly manner. But the important thing to know is these two things are two ends of a single relationship. You can't duplicate them any more than you can duplicate the one end of a piece of string. If you have a right, you can't turn it into two rights without making some agreement with the computer. And the computer can't just throw away the duty without receiving the right, because they have to be created and destroyed at the same time. So that's the right-duty relationship, and that is something that we can keep track of as if it were a coin, as if it were something that goes on a ledger. So the token looks kind of like this. It's something that we can hold to prevent change. We can't duplicate it, but we can move it around. We can give it to the computer gave it to us. We can divide our program into pieces and move it from one piece of the program to the other. Each subprogram can keep its own ledger for which coins it owns. There is another side to this token, which is that we must give it back if we want the thing to change. So this is actually a lock that prevents having two writers on the same object at the same time. The same thing that Rust was trying to check for. Again, don't believe me when I talk about Rust. These, and they have this thing-like nature that comes from the relationship, which makes them the sort of thing that is amenable to double-entry bookkeeping. Now, there is a second sort of interaction that we have, which is a little more complicated. We have an interaction with the computer where we say we would like to be told the value of our variable. Now, the computer wants to know whether it actually promised there was a stable value. It's like, oh yeah, we've got a token. The computer wants to be shown the token. But if we give the token back to the computer, it can change things. That's the rule. So we need some way out of this mess. And there's a trick we can apply. We're going to drill a hole in our token and use the bit of metal that we saved to make a different token to hand back to the computer that symbolizes the fact that our change token is now disabled. So we give this other token, the yellow circle, back to the computer. It sees it, hands the value and that token back to us, and we use that to fill in the hole. We're back to where we started, but now we know the value. Hofeld also studied this sort of relationship. I wouldn't have gotten it if I hadn't read Hofeld. This is an immunity-disability relationship. These are legal terms. Not necessarily legal terms that every lawyer subscribes to. There's considerable variation. But this is an immunity-disability relationship. We gave the computer an immunity. The immunity assures the computer that some other token that we have won't go away. It says we have a token and we will continue to hold that token until that immunity returns to us. We are promising that we won't write to the variable. We won't ask the computer to write to the variable while it is reading from the variable. The disability, on the other hand, is the other end of that promise we made. We promised not to let go of our token. Our token is disabled in a certain sense. We can't use it for writing while the immunity is out there. So immunity tokens look a lot like write tokens. They do prevent change. They are not duplicable. They are transferable, but we are going to limit transfers to you can issue them to some other part of the program and they can give it back to you, but they can't pass it along. So it's just 2 trips for an immunity token. So it acts a lot like the write token on this side, but not on the other side. It is not valid for change requests. You can't hand it to the computer when you ask it to change the value of something. And those are our 2 kinds of tokens. We have the write token, which right now has a hole in it. Why does it have a hole in it? That's a disability. If there's an immunity, there's always a disability. If there's a right, there's always a duty. These things are always counted the same. They're just on different books. There is one more thing that we can do with these, of course. We can drill holes in our tokens in order to say we won't move them, and we can hand those out. And it turns out that the immunities we get from putting another hole in our immunity are just as good as the immunities we get from putting a hole in the right, because they do symbolize the fact that they do imply that the right isn't going to go away while you hold the immunity. The total number of holes is always equal to the total number of immunities. And the right can't go away until all the holes are filled. So those are our 2 kinds of tokens, and we can keep track of them with bookkeeping. So here's a sample function. Took swap. I threw away all the template gunk because I'm not interested in that today, but this is a pretty basic implementation of swap. And we can open the books on swap. On the way in, we need to get credits for 2 objects, A and B, from our caller. And when we get credits, we add them to our balance. And when we declare the variable C, we get credit for C. And we add that to our balance. When we do a complicated operation like a function call, or pretty much most operations, they actually come in two phases. There's the call outward and this call inward. The call outward is a debit. Even an assignment starts with a debit. The debit for an assignment is one right to the variable C and one immunity for the variable A. And we have to cover that from our balance. So we are left with A with a disability and the right to B. End of the assignment, we receive credits very similar to the ones that we sent out. We add them to our balance. We're back where we were. Next assignment, same deal. We start with the debits and we cover them from our balance. We end with the credits. After the assignment, we have the credits and we add those to our balance. Same deal, third assignment. 3 assignments here and we are done with swap. Well, we're not quite done with swap because there's a kind of implicit operation going on here where C goes out of scope. C going away is a debit. So we take C off of our books. And there's another one. We return to the caller. The caller wants A and B back. So that's a debit. We have debits to our caller on the way out. And we cover those from the books. We're left with empty books. This is a good balance sheet. This means we wrote swap correctly. There are some things that could have gone wrong that didn't. I don't like to show you bad code. I'm going to show you some good code. But I will let you imagine that there was a debit that we couldn't cover from our balance. We don't get to use negative rights. This is simple math. This is if you have 2 apples, you can't give somebody 3 apples math. So if there is a debit we can't cover, we can signal an error. Just trying to make that debit signals an error. There's a second way things then can go wrong. It's a little subtle. If we get to the end of the books and our balance isn't empty, that means we had a resource leak. We received a promise that we didn't manage to pass on to anyone. That's a resource leak. Somebody out there has a duty that we would strand. So that's how we check our balance sheet. For every debit, did we manage to cover it? And when we return to our caller, after we hand them back the things that go back to our caller, after the final debits, is our balance sheet empty? And that checks, again, I'm going to say something about Rust you shouldn't trust. That checks the things that the borrow checker checks. But we can do this as a runtime check in the contract style. So there are some neat extensions that we can put on this. We can put marks on the tokens. I can put a mark, a little asterisk, on every token that does not need to be initialized, that represents a variable that does not need to be initialized. And so if I do that, sometimes we will have one of those on our balance, and some operations, like assignment, can take a variable that doesn't need to be initialized and still work with it. And if we add to our rules, you can't cover, you can cover an asterisk token with a regular token, but you can't cover a regular token with an asterisk token. The ledger now checks for whether or not we are accessing, whether or not we're reading from an uninitialized variable, because the things we read from never have the asterisk. The debits for the things that we read from never have an asterisk on them. We always have to read from an initialized variable. So this actually extends to all sorts of data that's not usually in our program. The information we needed to know whether we're following the rules, if it's not in our data itself, we can put it on the ledger. And then it's available to check debits and to check the empty ledger when we close it. There is a hitch, however. This isn't the whole story of swap. I'm a little surprised that nobody interrupted me and said, there's something else going on. There's something else going on. In C++, we allow an object to be swapped with itself. Maybe that wasn't a great choice. Maybe another language, Rust, would decide that it is completely unsafe to swap an object with itself. But that's not the choice that we made, and that ship has sailed for us. If we want to keep using swap without changing an awful lot of code, it has to allow an object to be swapped with itself. So if we're swapping an object with itself, we have a very different balance sheet because we only got one right. There is only one object coming in from the caller. Now, the beginning of the balance sheet looks pretty similar. This is just the same. When we get to assigning A to B, this is a self-assignment here. Self-assignment looks different on the balance sheet because we are only debited one right. We can't be debited a right and an immunity. We wouldn't be able to pay that. Also, the right that we are debited, we have to give, if we're doing a self-assignment, the thing we're assigning to has to be initialized because we can read from it also. So self-assignment looks different on the balance sheet. The last one, B equals C, remembering that B is the same object as A, looks pretty similar. We can just do the same thing we did before, and then C goes away, and A goes away. Once again, there's a difference in our balance sheet. We only return one object to our caller when we're doing a self-assignment. We need to support this. It is not a practical decision for C++ to say, nope, you can only have the other thing. So how can we do that? The answer is we can write code that explains which things are transferred. And when we do that, we can put an if statement in it so that different things get transferred depending on conditions that we can actually test at runtime. So here we have if the address of A is different from the address of B. That is a real data, not a ledger data comparison. We can just execute that to see which branch we're going down. And if they're different addresses, we have to have two writes. We have two objects, we need two writes. And it's two writes in, two writes out. But if it's the same address, we're only going to transfer one write out, one write to the function, and one write goes back when we return. We'll throw in a little extra thing for the ledger. We'll just tell it that when you use B, look up the write for B in A's column. So we can put the information about what references refer to in the ledger also. So we'll record references in the ledger, and we'll say, okay, this is the column, you look up the write in. So with that, we can have either balance sheet. We're going to choose one or the other at runtime, depending on whether we're swapping something with itself or swapping a thing with a different object. And the same thing applies to assignment. Assignment has this weird interface where we can assign from a thing to itself. And maybe that was a bad idea. Some other language might decide, no, you can't assign from a thing for itself. But again, that ship has sailed for C++. We want to allow objects to be assigned to themselves. We also want objects to be, we want uninitialized objects to be able to occupy the left-hand side of an assignment. That's important to us. So this is how we can do that. We can say, look, we're going to decide how many objects the assignment affects by comparing the pointers. And on one side, it's 2 objects. One of them only gets the yellow token. That's the const b syntax. I don't know about that syntax, but and we'll put a note on A. Maybe that's uninitialized. It's not the default way to transfer A. But if the pointers are equal, we only have one object, one reference. Object has to be initialized. We can put all of that in here. And this, of course, we can build into the compiler. The interface for swap, we can write that without actually touching the code for swap. The code for swap didn't change. We just explained how that code interfaces to other code. So can we do a bit better than that? Turns out we can. We can do all sorts of stuff now, especially if we tailor these tokens a little more closely to C++ semantics. Because I've been talking about tokens that represent that promise that the value of an object won't change. And we have 3 writes involved in swap. 3 writes to the duration, to the value, that last for the duration of one value in the object. And we can mark it up with a little bit of information. We can put, is it initialized? Yes or maybe. Yes or maybe is actually the one that matches our interfaces. It's not a yes or no question. But we have several other kinds of stability promises in C++. We have promises of lifetime stability. Now, swap doesn't mess with the lifetimes of A and B. It doesn't need writes to that. It just needs to know that it's accessing A and B within their lifetimes. So it gets yellow tokens for the lifetime of A and B, but a blue token for the lifetime of C. The lifetime of C is begun and ended by swap itself. And we can put some notations on it. We can put a notation on this for, is the thing actually declared const, in which case extra rules apply. Now, those extra rules won't affect you very much if you just avoid const casting. So my advice is, get your code const correct, don't use const cast. You don't have to worry about this rule. But if you can't do that, our ledger can have your back. It can check for whether you are doing a modification of something, you're attempting to do a modification of something that is a declared const, and which would be undefined behavior. We can also issue separate tokens for the duration of storage. Duration of storage is not directly tied to lifetime in C++. We can destroy objects without giving back their storage. We can create a new object in that storage, and the old pointers and references will refer to the new object now. So we have a possibly wider lifetime. Again, you're doing weird tricks at this point, or you're using unions. But we have a wider lifetime for storage in C++. And that token is actually a great place to record the beginning and end of the storage. We can keep track of that on the ledger. Just have that available anytime somebody is trying to access that storage. I see a question.
Yeah. If I'm correct, in the C++ standard, as a storage, once you destroy an object, you cannot use the same reference point as the old one.
You are not correct in all cases.
Okay, thank you.
The question was, is it true that you can reuse the old pointers when you destroy and recreate an object in the same storage? Sometimes that is, if that is true, in the case where you can't, I would say that's new storage. In the case, by my definition. But there are certainly places where you can destroy and recreate, and we bless that. Yes?
This not declared constant thing that you were talking about seems to me pervasive reference semantics in C++. If you want to actually even do that at runtime, it implies a side table where you're tracking the mutation of all objects in the system. Because you can escape through any arbitrary amount of pointers that aren't visible to the interface of your
so
function.
Dave suggests that this middle one would require a table that keeps track of everything that is const or not, a sort of grand ledger that would apply to the entire program, and he's wrong. This is the promise that one part of the program makes to another that something is not in fact declared const can be written on the lifetime token and just transmitted from one subprogram's token to another. Now, it doesn't mean that some other part of the program has not broken its promise. That is, the ledger is checking local properties. If some other part of the program is breaking its promises, is telling people that, or is not covering its debits properly, that's still a bug in your program, but it's a bug in a different part of the program that needs to be caught by the ledger for that part of the program. Dave shakes his head, but he's wrong, and he's going to shut up now. Sorry. You don't have to leave. So the storage boundary here is something that we can store on the storage tokens, and we can make that useful. When we have a value of a pointer, we can store which ledger column the pointer points into. That is, we can store the information we need to find out what token we use when we dereference that pointer. I'm going to add a little thing there. The generation is a number that we can add in case we want to reuse a ledger column. Once the storage for a pointer, or the storage for an object has gone away, we might want to reuse that ledger column. We can bump the generation, and then we would know when you dereferenced that old pointer that it refers to old data that doesn't exist anymore. We can catch that error before we actually go look at that data. So, that is the sort of thing that we can put on a ledger, all sorts of stuff for following the rules, the information we needed to follow the rules we're trying to obey that wasn't actually in the values of our tokens, of our variables, can be recorded in these tokens that represent the duration of that information. So let's look at another couple of functions. Here are some maybe familiar functions from the standard library. Again, I threw away all the template gunk because I'm not interested in it. We have iter swap and reverse. And I've provided some sample implementations here. The thing that's interesting about iter swap and reverse is that these functions are twins. You couldn't tell the difference between these functions if they didn't have different names. Now, Again, you might argue that this is a bad idea. Iter swap and reverse use their parameters in very different ways. Iter swap has 2 pointers, and those pointers point to 2 objects, or maybe the same object, but not a whole range of objects. Iter swap is just about 2 things being pointed to. Reverse, on the other hand, is using its parameters to denote a span. You're trying to refer to this whole range of objects. B doesn't even necessarily point to anything. It could be the one off the end pointer. So very different use of parameters. You might say, well, you have very different use of parameters. You should have very different parameter lists. Reverse should probably take a span as its argument. But it doesn't. That ship has sailed. This is the reverse that people are using. And we need to support people who are using the existing functions. We don't want to tell everybody who's using reverse at the moment that their code cannot possibly get a gold star. So, what can we do about this? Again, we can write interfaces that explain how iter swap and reverse are going to use their parameters. So, for iter swap, the key to this is knowing that we can transfer things that are not parameters. In this case, we again have a branch because it could be self-swap or not. We decide whether it's self-swap by comparing the 2 iterators. But we're either going to transfer 3 writes in the case of self-swap, or we're going to transfer 4 writes in the case of swapping 2 different things. Because we need to transfer the writes to the pointers, which iter swap here is allowed to change. So we transfer the writes so that it can change the pointers. Maybe it shouldn't, but we're not changing that about it. Yes?
I'm confused how is iter swap allowed to change the pointer? Say passed by value. Like, what do you mean by iter swap is allowed to change the pointers?
The pointers are variables that are available to iter swap, and it can assign to them. That's what I mean. You can assign to your parameters as long as in the body of your function you don't declare them const. So yes, iter swap is absolutely able to change the values of those pointers. But it is much more interesting. In fact, our implementation did not. Our implementation just read from them and dereferenced it. But somebody else's implementation could. Iter swap gets to change the values of its pointer. It gets writes, not immunities for them. But it also gets writes to the things pointed to. There might be 2 things pointed to or 1 thing pointed to. That's our branch. See another question?
In this example, when you're choosing one set of books or another based on A equals B or not, does the bookkeeper check your choice? Or does the bookkeeper assume your choice is correct and then check the rest? So like if I swapped the if and else bodies, and so I made a terrible bookkeeping choice.
So what would happen if you had written this differently and you'd swap the if and else and put the wrong thing on the ledger? Well, 2 things are going to happen. The caller's books will be affected. They will get a different set of debits. And we can check whether they can cover that set of debits that you didn't really intend. And maybe they can. And then the callee is going to get a different set of credits. And we can ask whether, as the callee executes, whether it can use those credits to cover the debits it has. And maybe it can. So what we're checking is whether or not the caller and callee are correctly behaving according to the rules laid out in the interfaces. If you write a different interface, you're changing the rules you expect them to follow, and maybe they do, maybe they don't. Honestly, I think if you swapped these, it would be difficult for particularly the caller to get the right thing, because you try to swap two different things and it'll say, oh, that's the same thing. Oh, no, you have one right, you could transfer one right. So the caller's initial debit would probably be covered. But the callee is going to call swap. Swap is going to say, I need 2 tokens. The callee only has 1 token. So iter_swap wouldn't be able to call swap if you got the interface for iter_swap wrong in that way. Also, right. Right, I wanted to say, I have put this notation when we transfer a pointer. I am saying, I'm telling which column it'll have to point into in a way that the other side can read. So actually, these transfers of the pointers would fail. You couldn't transfer 2 pointers and say they pointed to the same thing when in fact they point to different things, and that is something that the caller could check. So, yeah, there are a few places where things would fall apart if you get your interface wrong. If they don't fall apart, it means that your function actually does, that you're actually behaving fine despite the fact that you wrote things wrong.
That's my favorite kind of code.
Yeah. So that's iter_swap. And we'll move on to reverse. In reverse, you remember how I said that it would have been nice, maybe, if reverse had a span parameter? We can make a span up here inside the interface in reverse and just say, yeah, that's what you get. We do have an issue. The actual type span has a weird mixture of pointer and reference semantics. This system works a little better if you're using types that clearly are reference-like or clearly are pointer-like. So I'm using a different type. It's very possible that we will decide that span is reference-like enough that we'll just use it that way, but that'll be syntax and decisions to be made later. So I'm going to invent a type span ref, which is like span, but entirely reference-like. You can't change it to point to something else. So what we're going to do is when we transfer that, we transfer the stuff it's going to point to. And we will also transfer the pointers A and B. And again, we will give the other side a hint about what they point to. This one will point to the beginning of the span. That one will point to the end of the span. But the interesting thing is this span thing. If somebody gives you a span of 1,000 objects, 1,000 integers, you don't want to put 1,000 entries on the books. You put one big entry on the book that says all of these things arrived. So we have credits that are bulk, great big credits that can be recorded in a single line on the ledger. And that will save us a lot of time. It will keep us from getting the complexity wrong in our interfaces. We can run our interfaces generally in constant complexity. Yes?
So reverse got the rights for A and B. When S was created, it was allowed to create the rights for everything in between A and B?
S is, when S is created, it creates the right to the span ref. It's Okay, now I have a reference. It's just like creating any other reference. What this transfer is saying is that in order to call this, the caller has to provide these tokens. It has to provide the rights to everything from A to B as three big tokens. So the caller is responsible for this. This is debit to the caller, credit to the callee. This is just what's moving from the caller to the callee. It's not created, and we can say that because span is a reference-like type, and creating a reference doesn't create the thing referenced. Yes?
But if you have one token for the whole thing, but inside you call swap, which is what reverse does, which requires tokens for individual elements, how does that?
We're getting to that.
Okay.
And it's right. It's like, okay, we have these big tokens. How do we use a great big token when inside of reverse, we're going to be doing a lot of swapping individual elements? There is another bookkeeping technique that you may be familiar with, making change. If I have $1 and I want to pay somebody a quarter, I need to make change. So when we see that we are subtracting, we're doing an iter swap of two different things in this case, because I wrote reverse in a way that it never does a self swap. So we're doing an iter swap, two different objects. We are debiting two tokens. How do we do this? We subtract them by making change. When we need to hand out the right from the right to the P to P+1 range, we just break up our right into smaller pieces. And we have this combination of two ranges on our balance sheet. And when we need to hand out the right to Q, we make change again, and we've broken it into even smaller pieces. In practice, we will probably need types that represent, plain range, range with a hole in it, range with two holes, range broken into two parts, range broken into three parts, and so forth. But it's just a matter of having the types available to do the math that you need to represent the things that are left over. And this is not hard math. We know how to make change for a range. It's like, okay, I give you this bit in the middle. I still hold the thing that came before and the thing after. And since we know which columns these things are coming from, we know where to look for this when we do the subtraction. This actually comes up in a second place. This comes up in a second place, which is a little more subtle, which is iter swap also does pointer arithmetic. And it turns out that pointer arithmetic needs a certain guarantee. If I'm going to increment a pointer, I need to know that the storage that the pointer is skipping over exists, because otherwise I couldn't guarantee a pointer that has the correct provenance. So if I'm incrementing P, I need an immunity token for the storage that for the 1 unit after P. But the balance we have is the entire storage range from A to B. How does that work? Again, we make change and we hand out the immunity from the bit in the middle. So we break it into 3 pieces, put a hole in this bit in the middle. And that's how we do it. When we get that token back, we fill in the hole. Sometime later, in order to keep our bookkeeping tables from growing and growing and growing, when we go around a loop, we will have to coalesce things back into big tokens, because it's a really nice property to have that when you go around a loop, you end up with the same amount of data that you had before. That's how local variables work. That's why we don't have to go to the heap to store local variables. So There does have to be an operation that is the inverse of making change. We know how to do that operation. We know how to turn 4 quarters into $1. I don't actually have a word for the inverse of making change. If somebody does, please tell me. But
in
what?
casinos, it's coloring up.
It is
Coloring up in casinos. You take small chips and turn them into big chips.
Okay. So apparently in casinos, the term is coloring up because smaller chips have a different color than bigger chips. So yes, we have to be able to do that. But if we can turn our smaller chips into bigger chips, we can ensure that as we go around the loop, we don't expand the amount of storage we need for our ledger. Our ledger becomes something where the amount of storage can be calculated in the same way that we calculate the storage for local variables, which is really nice. Our ledger is like just a bunch of local variables. So stepping back a bit, we have our function body, and there's a data flow into our function body when it's called, outward when we call something else, back in when the thing we call returns, and out again when we return. That's the data flow involved in our function. And what we are adding to it is that at the beginning of the function, we will open a ledger. And on the way in, we will fill in credits on that ledger using the data that's flowing into our function. The data flowing into our function determines what credits get added to our ledger. When we call a function, the data flowing out of our function determines what debits get recorded on our ledger. Coming back, we get credits, again, calculated from the data flowing back into our function. And as we return, we have debits that flow outward. Notice that debits can create error paths. So we might have discovered some error if we couldn't cover a debit. We can also discover an error when we close the ledger. We might have something left on the ledger that we should have given away and didn't. We could have a resource leak. It is true that in addition to this, the making change and I guess coloring up both are things that could fail. It might be not possible with the tokens you have to make the change necessary to cover a debt, and it might not be possible to combine the tokens you have into the bigger tokens once you've gone around a loop. Those are 2 more error paths. But I want to point out that these error paths are just ordinary code. This is all code that can be emitted by your compiler. And the data involved in the ledger is a very special kind of data. It's got the properties of local variables. That is, there's a limited amount of it. It's created and destroyed internally. It is never seen by another function. This stuff never escapes your function. And mostly, it's set with a bunch of constants. It's just, I received this token. It had to be initialized. It's mostly that stuff. This data is an optimizer's dream. And it's very possible if you write your program, if your subprogram actually doesn't have errors, if it's not going to trigger these error paths, it's very possible that your optimizer might be able to remove them, particularly since you're probably not intending to make your code so complicated that even your optimizer can't follow it. So it's very possible that the optimizer can remove the error paths. And when the optimizer removes the error paths, the whole rest of this folds up because of that one-way data flow. None of this was necessary anymore. And if you can do that, if you can compile it with the ledger, with all your ledger checks on, but your optimizer can remove all of the ledger checks, all of that ledger stuff, that's actually a proof that as compiled, your program didn't have any of the errors the ledger was checking for. And I think that says something special about your subprogram. I think that if the optimizer removes every ledger error path, your function should get a gold star. So I do like to step back. Oh, I have a...
That's okay. So ledger never tracks anything across function.
The ledger never tracks anything across function. That is the wonder of double entry bookkeeping. Debits to one function, credits to the other. Every function gets its own ledger.
Lisa?
Oh, there's...
To get a gold star, does your optimizer need to remove your part of the ledger from the caller as well?
The caller has no part of your ledger. You get a gold star, you have one ledger, your caller has its own ledger. If there is something that the optimizer can't remove from your caller doesn't get the gold star.
Mm-hmm.
And this is almost equivalent. Again, I'm going to say something that you shouldn't trust, but this is a very similar check to what Rust is in fact doing. Rust is not checking that your caller didn't do an unsafe thing and lie to you about where things are and how many objects you have rights to and so forth. That check is not part of the check that happens to your function. Again, don't believe me when I talk about Rust. So this is a local check. And what you would like to do is have this check be so all across your program, because they knit together very nicely through the wonders of bookkeeping. So I do like to step back at the end of a talk and say something about some lesson that's some deeper lesson involved. Yes.
So a lot of what you've just covered seemed like information you could know statically. And some of it seemed like runtime information that you wouldn't know statically. I'm curious how much of it is possible to determine in compilation versus at runtime.
So the question is, how much is possible to determine in compilation versus runtime? So every bit of this is filled in by runtime data. You know, the runtime data tells you what credits and debits go onto your ledger. So you don't know that at compilation time. But the flow between different parts, you do know. And of course, everything that was filled in by a constant, your optimizer will be able to see, oh, that was a constant, that's easy. And it can track data flow. So it doesn't know which branch you're going to go down when you compare those pointers. Because at runtime, you could go down either branch. But optimizers are capable of checking both branches and saying, oh, in both of these branches, that data doesn't lead to anything, I don't have to store it. Yes?
If the optimizer doesn't remove the ledger, does that imply anything about the correctness?
If the optimizer doesn't remove the ledger error paths, does it imply anything about correctness? It implies that showing correctness was too difficult for the optimizer, which does not mean that your program was incorrect, but it does leave the possibility open Presumably, you also thought about these things, and you thought your program was correct. So you might have been right, and it was just too complicated for your optimizer to see. I'm going to defer all questions at this point till I finish the talk. So I want to step back just a little bit and talk about a lesson that is inherent here. And it's one that I think I really understood through the time I was lucky enough to work with this guy, George Lakoff, noted linguist, author of Metaphors We Live By and Where Mathematics Comes From, amongst other things. And Lakoff is famous for his study of metaphors, not as a poetic device, but as a cognitive device, as a way to reason about the world. He contends that metaphor applying metaphors is a fundamental part of human reasoning. And he may very well be right. It is certainly true, however, that the world we live in is rich with solutions. And I don't just mean that it is mostly covered in saline. What I mean is that for a very long time, a lot of smart people have been solving a lot of problems, and our culture has kept records of this. It is true, we can look back and see things that in, 700 years ago, people were using double entry bookkeeping to keep track of things that they couldn't just go out and count. 100 years ago, legal scholars were interested in figuring out how to describe the relationships involved, particularly in property rights. Property rights, by the way, being what was being kept track of on those ledgers. I haven't read them, but I'm willing to bet those were property rights being kept track of. The world is very rich with solutions, but we need a good metaphor to let us apply them. We need to be able to say that the thing in our program is like the thing that that Hofeld was writing about, like the thing that was being recorded in that Florentine ledger. So metaphors are what lets us apply these old solutions. And with that, thank you for listening. Are there any questions? Yes.
So how does this interact with structs? Do they hold their own tokens, or are those accounted like a constructor-destructor sort of thing?
How does this interact with structs? Okay, so I would really like to get this into the talk, but it gets a little complicated. Change-making turns out to be intimately tied to an object, a view of the world that involves complex objects. Because you can think of a structure either as a single thing or as a collection of individual things. And if you're thinking of it as a single thing, then you need one token. If you're thinking of it as a collection of individual things, because say you want to modify a particular member, you can break the structure into individual member tokens. Much the same way as you can break a span into subspans. This is a neat place to hook in class invariants. Because I can say, when I make change, when I can say my whole class token can be annotated with, yeah, this satisfies the class invariant. And it just represents a class a whole class object that satisfies its invariant. When I break it up, what do I get? I get a whole bunch of members, and I get post conditions of the breakup event that tell us that all of the individual parts of the class invariant held. When I go the other way, when I do coloring up, that was the term. When I do the reverse of making change, I need to supply all the parts and meet the precondition that they meet the class invariant, and then I can put that together into one big token that satisfies the class invariant. And if our class has some defective state that is important to us, like being uninitialized, being in the moved from state or something, we can say, I'm not going to mark that with the regular invariant mark. I'm going to mark that with, the maybe defective mark. And some functions just won't accept things that might be defective. So that is how we can reason about structures, and it neatly incorporates class invariants. Yes?
In some of your examples, the interface description is almost as big as the code in the function. When we're considering backwards compatibility by annotating a set of functions in order to keep like a billion lines of code still compiling, probably worthwhile. Have you given any thought, at least in new code, for ways that the interface description could shrink or disappear entirely if you use the appropriate types or something that's a little more obvious to the compiler?
Yeah. Okay, so the question is, can we make the interfaces smaller because they're annoyingly large? The length of the interface that you need really depends on two things. It depends on how complicated it is to explain what your function is doing in all the cases. So, for example, if we just banned self-swap and banned self-assignment, that would have shrunk my interfaces a whole lot. If you write functions that are nicer, that don't need if you write functions that don't need complicated interfaces, you don't have to write complicated interfaces. The other thing that we could use to shrink it is having some conventions. We could have, and in fact, when I first started writing this talk, I'm like, okay, I'll talk about no, I don't want to talk about the conventions. That'll add more complexity to the talk. No one will follow it. But you can have a convention that says, look, if I have a reference parameter and I don't actually talk about what to transfer for that reference parameter, the default is I transfer the right or the immunity depending on whether the reference is const. And I just get the right thing most of the time automatically. Wouldn't have saved me from writing that if statement, but it would have saved a few lines in the in swap and inter swap. But so you can have conventions like that with a way to break it to say, I'm passing a reference, but I'm not actually passing the object, or I'm passing some weird thing that is not the expected thing. So you can have a way to just look at the signature of a function, or the parameter list and the return type of a function. You can have a way to look at those and determine defaults for the interface. And if your function just follows the defaults, maybe you don't have to write anything at all. In fact, another language that I really shouldn't talk about pretty much works that way. Everything is coupled to how you define the interface for your function. Your parameter list determines what credits and debits you have. We have to decouple our parameter list from the debits and credits because our parameter lists weren't designed with that in mind. But If you have types that already express the correct debits and credits, and sometimes we do, we have things like span, we have things like unique pointer. Unique pointer actually transfers a complicated thing. That's okay. So if you have types that transfer the right things, then you can just use them in your parameter list and accept the defaults. And unless your function is being a little weird, you got it right. So I seem to be out of time. So I will take further questions in about 10 minutes in the coffee area.